You joint ventured, you were part of a consortium that developed this product, including STMicroelectronics, which is a gigantic company. Can you tell us a little bit about how you came to work with them and what their reaction to it all was?
Project is a French granted project because, in France, we have a lot of nuclear power. In USA, you have more nuclear reactor, but like most of our electricity come from nuclear power, for 70% or something. Because we have a lot of nuclear power, we have a lot of nuclear waste. And we need to find a way to reduce the amount of this waste and let's say both, get money from this waste. So revalorization of nuclear waste is a main objective of French government, especially with the new nuclear, which will come in the next decade, 10 a year or something. So there is a lot of grants for a company like us in order to find a way to use nuclear waste or to improve the nuclear waste cycle. What happened is Betavoltaic 10 years, not 10 years ago, maybe 7 years ago, start to appear. In US, there was one startup, which was NDB, if I recall. In UK, there was Arc and Light. So Betavoltaic just start to re-emerge from a long black period because it come from the 70s, but after nobody wanted to use it. But all this Betavoltaic have in common the diamond, and we'll speak about it later, why diamond and not other materials. But STMicroelectronics, which was aware about everything happening in semiconductor world, just say, okay, let's try to do the same. Go to France, say we have a way to use nuclear waste doing Betavoltaics. Because it's French, they said like we need to find an actor with very good semiconductor, diamond, so a very very good semiconductor, and they were looking, and DIAMFAB just have been created. Like the DIAMFAB company emerged in 2019, and the project started in 2020. Like writing the project. So they contact us. They are in Grenoble. We are in Grenoble. It was a team of STMicroelectronics from Grenoble because they are specialized in radiation hardness and things. They are working with a lot of different companies. So they contact us and say, okay, we need diamonds and we need a third actor because none of them and none of us know how to use tritium. So they look into it, and CEA. The Commissariat à l'Énergie Atomique, so the French, it's a French public and military and a little bit private, but okay, it's a French big organization, is using tritium because of Cadarache. So the project with the tokamak, like a fusion reactor in Cadarache, south of France, which a lot of countries participating. So they are using tritium because tritium can be used for fusion. So they know how to use it. And there you have like 3 French entities with good knowledge on the 3 parts of the project. So DIAMFAB is doing the diamond, of course. CA is handling the tritium, and STMicroelectronics is doing the harvesting solution. Because that's nice to have a generator, but then you need to put it something useful. So an harvesting solution coupled with a battery and things for dedicated application, industrial IoT, civil engineering, space application. Like the sky is the limit. But there was it was a consortium with 3 entities, and it's how it works, how it's emerged.
Is it the case that STMicroelectronics will be distributing it commercially with their applications? Is that already something that's being worked on?
The origin of the idea is we are a foundry. We will supply diamond to build it. It wasn't a bit unclear of whom will handle the tritium part, if it will be another company, something created from this, or STMicroelectronics diversifying things. And ST, yes, was and still is the commercial pipe in order to reach clients, because we are a very young startup. We are not able to find clients. We are a little bit actor of the nuclear world, but not as such. DIAMFAB have many objectives, and Betavoltaic is one. We are not fully dedicated on nuclear, therefore we don't have the same shared contact and space. And ST being the big company it is, like you know how to find clients and to sell it and package it and find regulation which will work with such kind of devices. In your question, there was the imply of actually, like I want to precise that actually our batteries are not sold. We can sell maybe one if needed, but it will take time to do regulation and all of this. But we don't have an industrial tool ready to build these batteries. We are trying to develop it. Okay, it will take time, but actually the technology is working. We know how it works. We show that it works. We know that it's possible. We did it. But to do an industrial and scale the production, this is something which take a lot of time and a lot of money. So we are still working on R&D to improve capacity, because like this, you get a more performant device, and also on the industrial part with our partners, so STMicroelectronics, and for now STMicroelectronics. But if we find another partner, it will be nice, especially one good with tritium handling.
Yeah, I imagine scaling is expensive, and you have to figure out the best ways to go. It seems on the surface anyway that the commercial possibilities are pretty vast. If you think about all of the harsh environment places where the generator can be used, there's significant opportunities for it.
Yes, and even more than harsh environment, the best thing is the time of life, like the lifespan of the batteries. So in some place which are not really harsh environment, 20 years of operation life can save a lot of money. We know that the markets, let's put a S, because like there is many different markets that can use this device. We know that they are huge, they are vast. It's just that we have to keep in mind that it's a nuclear object. Therefore, we need traceability, we need nuclear safety, no possibility for environmental contamination, even though tritium is a very safe radionuclide for human and fish and for environment, because like hydrogen is not something which accumulates in the body, and the radiation is low energy, so damage are very low and accumulation is low. Therefore, nuclear risk is lower, let's say, than a lot of other radionuclides. Still, it's a nuclear object. In order to commercialize it, but you need regulation. You need it will depend on the countries, of course, and you need also like the public to accept such kind of technology. So as I said, with tritium, it's easy, not easier, but it's less harmful potentially. So we think that the public can accept such kind of technology because this one is it's safe, let's say. That would not be the case if we change the radionuclide, which is something we can do. You choose a radionuclide in function of your application, so time of efficiency. If you look at Chinese companies, for example, they wanted to do a battery which will last 100 years. It's okay, 100 years seems gigantic, and that seems very nice. Why are you using a battery for 100 years? Is there application for 100 years? I don't know. And it's working with nickel, and nickel is something which is bio-acceptable. So therefore, you can accumulate it in the body. So if you have like contamination, you can contaminate the food chain, and that's different. But for one application which need 100 years, Chinese battery, the Chinese approach will be good, but we are also able to do it. It's just that we don't have nickel. So
why was technology grade grown diamond so important to this development? What were the material properties and your own expertise in growing diamond? Why was that so important to this project?
So as I said, Betavoltaic exists since the 70s. in the 70s in US. They implant, in fact, Betavoltaic as a cardiac stimulator, and it worked. It worked, but they used silicon at the time. Then you have silicon carbide, which appear, and now diamond. It's a natural evolution of this material. And why diamond? Because as you increase the gap of the semiconductor, so silicon have a little gap, silicon carbide have average gap 2.3 eV something, and the diamond is twice as like the gap is 5, so it's ultra wide band gap. It's something for semiconductor people who it's something we know. Anyway, as you increase this gap, the efficiency of the conversion increase. And for example, for silicon, efficiency was about 6 or 7% in PN junction. So in the junction with the highest field possible. For silicon carbide, it's maybe 18%, and for diamond, the potential can reach 28%. It has been shown in by different team. It was a Japanese team, if I recall. Okay, this need a PN junction. We are not at this state now because there is some problem with the PN junction with diamond. Everybody in the world is working on PN junction, and someone will finally find a solution soon. Everybody know that. It's just that there is a little lock. It will be done. But diamond have 28% potential efficiency, which is very nice because you can reduce the radioactive charge, and also by your radioactive material have a cost. Therefore, so you can reduce your cost. So that was one point, the efficiency of the converter. And the second point is the ability, like intrinsic properties, let's say, of diamond. Its radiation hardness. Diamond is a very low, it's carbon. Carbon have a very low atomic number, 6. And because of it reduces the number of interaction possible from the radiation with the nucleus. Why it is important? Because like when electrons, like the radiation, interact with the nucleus, first it can do damage to the material, and this damage will reduce the lifespan of the converter. Diamond is very hard for that. Like it's very difficult to move carbon atoms. Therefore, you increase the lifespan through years, and also it's the emission of Bremsstrahlung. It's a German word, and everybody is using it, but it's like the continuous breaking radiations. Okay, anyway, when an electron is breaking, like removing its energy near the nucleus, it can produce a gamma ray, so a photon, which is hardly screened. It's very hard to screen, so you need like fixed shielding for that. And diamond, being very low wave, low atomic number, it produces way less Bremsstrahlung than its counterpart. Therefore, for let's say high power, something which is massive, you need less shielding. Therefore, you win in wave and cost. So diamond is let's say the best candidate in all the semiconductor we know. Like it cannot go better than with diamond. That's why everybody is trying to do Betavoltaic with diamond. Betavoltaic with silicon already existed, sorry, in the past, but with diamond is better. And now properties are expected to be good enough to be an object which is commercialized for IoT, for industrial IoT or space applications. Now we think like it's mature enough to go to the market again, let's say.
And the economics are getting better too. Previously, people would have never thought about using diamond because it wasn't really commercially viable.
Of course, the price of diamond is decreasing year after year. Size of diamond increase, price of CVD diamond, like the artificial diamond. So semiconductor industry see a decrease of like the let's say the wafer, so the raw material, the first brick, like we see a decrease every year, every 6 months even, and the size is increasing. Now you can find commercially available 2 inches wafer. It wasn't even conceivable 3 years ago. 3 years ago, it was like, okay, you get this. And so now, like, it's become more and more an industrial viable option for semiconductor, especially for high power, which is the other part of like the main objective of our company. But everything is depend on this disponibility of diamond.
This is fascinating. Are you working on anything else interesting that you can share with us without breaking any secrets?
Our company is working on many projects. Most of them implied power electronics. We are working not only with STMicroelectronics, we are working with Murata, with Schneider Electrics. We are working on developing, so there's 3 key components, as I said before, diode, field effect transistor, and condensator. Soon there will be some news about them, but that's not my work. That's the work of my colleagues. I will leave the honor to maybe in this podcast. Maybe they can speak about it later on. But for nuclear batteries, we will have fresh news in this summer, okay, approximately, because we are doing another project with a different radionuclide material, this time for space, with ESA and Orano. Orano, which is some people know Orano, but Orano is the company which is recycling. Like they are implied in all the nuclear cycle of French, but also European nuclear industry. So they are producing the fuel, so enrichment, extracting the mineral from carry, and also recycling the spent fuel. So they have access to nuclear spent fuel, like to nuclear waste, and we want to use nuclear waste, of course. It's an important thing. And so we have a project with them, with Orano, with ESA. So very soon there will be something, but I cannot make a revelation. But it will come maybe in June and July.
All right. Well, we look forward to hearing about that. Really, really exciting work you're doing, and actually not just good for DIAMFAB, but also good for the planet. So that's excellent as well.